Thanks, everybody. Welcome to the session. My name is Zhang. This is a project done by me and my colleague Xiong. I'm from the Facebook software team in the Spark team, and Jie is from the Facebook S team. In this talk, we want to share our experiences in migrating the Hive workload to SparkSQL. High-level overview. We go through the motivation, then syntax gap analysis. Then we introduce our online and offline shadow framework. Then we drill down some detail for performance optimization. Last, we want to introduce the challenges we hit and the future work, because this is an ongoing process. First, why we want to move the Hive workload to Spark. Hive initiated by the Facebook provide a good SQL interface to the end user and the data scientist. But in Hive is built on top MapReduce framework. In each stage of the job, you have to go through the mapper, shuffle, reducer, then write into HDFS. Then in the next stage, you're reading from the HDFS again. Spark as a more advanced architecture. In the whole job, the job is constructed as a DAG. It's more computation efficient. And from the last year, our team started migrating some job, heavy pipeline from the Hive to Spark. And we observed some significant performance gain. That's the initial motivation for us to migrate the Hive workload to Spark. Also, we want to provide the Spark as a general service to all the Facebook developer and the data scientist. But when the user uses SQL language, they don't need to be aware of the underlying engine, either Hive or Spark. So do the migration definitely help us to identify the gap between the SparkSQL and the HiveQL. Then we can bridge this gap. Then when we have this general service available to end user, they don't care what's the computation engine. But before we move forward to make the decision to do the massive migration, we have to know how compatible between the SparkSQL and the HQL, because we have so many Hive workload already there for years. The first thing, we retrieved Hive query log, actually then use the Spark parser and the Catalyst engine to do the basic syntax analysis. We want to get the insights, the compatibility between these two SQL dialogue. What we did, actually, we run those queries, go through the parsing, analyzing, optimization, physical plan generation, and the executed plan. This is the initial data we get. The green bar actually is all the queries that can pass all the different phases. Most of the failure happens in optimization, followed by the analyzer and the parser. There are a small number filled in the physical plan. There's no query filled in the execution plan. But this number actually is quite encouraging. More than 50% can go through all the syntax analysis phase. It built up our confidence, but this percentage distribution is based on the number of queries. We also want to get more insights. With respect to the CPU computation, what's the distribution? This chart is quite consistent with the last one, but this is with respect to the computation cost. Still, more than 50% can go through the whole syntax analysis phase without any error. There's another good news here. There's a small number of syntax error actually take a big chunk. If we fix top 10 syntax error, probably more than 80, probably 90% can go through all the syntax analysis phase. With this number, we decided to start the project to the massive migration. The first thing we do the migration, we need to decide what kind of pipeline we want to migrate. We don't say that every query running in Spark, running in Hive, we want to migrate. If they perform worse in Spark, that's not what we want. or they have some impact, for example, correctness. So this metrics, the first one, the most important is the correctness. Of course, it's the second one, stability. All those pipelines running in production for months, even years. After we move to Spark, we have to make sure they are at least as same stable status. Our goal is to reduce the computation cost. The next metric is the reduction of the reserved CPU time. The reserved CPU time here means when we launch a Spark job, the Spark job will request resource from the resource manager. When those resources get allocated, Spark may not use it. For example, there's no task running in the executor, or the CPU is blocked on I/O. But because this resource is already allocated, it cannot be assigned to other Spark application or any other job. We still count this as the resource used by the Spark. The last one is the latency. For some latency-sensitive pipeline, this is a very important metric. These four metrics, we based on these four metrics to decide what pipeline to migrate. Overall, we build a migration framework. The first one, we have the offline scheduler. It retrieves the Hive query log, then run those queries in a specific resource pool. In our syntax analysis, we only analyze the query. We didn't really run the query. This step is quite important to make sure they are semantically equal, not only syntax. So offline, number one is check the semantic. There's no gap between the query. Also, we got the metrics in one of those jobs running in Spark. For example, the reserved CPU time and the latency. In Hive, we already have those logs. Then in Spark, when we run the query, we also get the log. Then we know whether they perform better in Spark than Hive. After the offline shadow, if those queries meet our criteria, then we move forward to put them into online shadow. Offline shadow maybe run the query only once or twice. We get the basic metrics. Online shadow is maybe, if not more important, at least equal important. They check whether this pipeline can run stably for a long time, also whether they can run consistently. Another important part is online shadow. They run the exactly same environment when we move them into production. That's quite important. After running in online for 2 weeks or even more time based on the importance of the pipeline, we check the metrics. If they are consistent, meeting our criteria, we move forward to put them to the Spark production. Otherwise, we actually revert back to Hive. There are some guidelines for offline shadow. First, we have to avoid affecting any production pipeline. So we get the same query based on the Hive query log. We have to rewrite the query plan to write into a different table. For example, we append a suffix to the table name and Spark shadow. We have to avoid absolute data because we have to verify those queries are semantically equal in Spark and Hive. We have to run those queries on the same source data as soon as possible, in practice 1 day after the Hive query. Because if we run it too late, the source table may already changed. The last step is identify the incorrectness earlier. We have the hash validation. Hash validation calculates the hash value for each column of the row, then generate the digest for the whole table. Then we comparing the digest between the Hive and the Spark output table. If they are the same, we are pretty sure they are semantically equal. They have the correct result. But hash validation is very heavy, sometimes even heavier than the pipeline itself, because we need to calculate the hash. So we have a lightweight method to do the validation. That's a count validation. We can't just simply count the row number of each table, then comparing the Hive table and the Spark table. If they match, we move forward with hash validation. Otherwise, we need to dig into it to see why the Spark result doesn't match. Here is some detail for offline shadow process. The first thing, we need to set up the dedicated resource pool for offline shadow. We don't want our shadow job impact the production pipeline. Then we select the pipelines with computation cost above some certain threshold. For example, we want to migrate those heavy pipelines first. So maybe the criteria is at least 100 CPU days or at least 50 CPU days. Then we launch the Spark application, continuously run those selected pipelines in the shadow mode. When we run those in shadow mode, we publish all those metrics to some dashboard. Then we pick up the candidates for online shadow using those metrics. In our online shadow, we also have to follow some guidelines. The first one, the online shadow has to be run exactly the same environment as production, because this is the last step before we switch to production. We don't want anything unexpected to happen. In online shadow, it runs for a long time, not like offline, it only run query once or twice. Here, typically, we let it run at least 2 weeks or 3 weeks. For very high critical pipeline, actually, we let it run maybe months. Then we check those performance number, the CPU time and latency, based on each pipeline that maybe have different criteria. Another important metric is this online shadow has to be transparent to production pipeline. No matter the online shadow succeed or fail, the production pipeline cannot get impacted. They are running in the same resource pool, the online shadow and the production. In detail, because all those queries are originally written in HiveQL, there is some inconsistency between the SparkSQL and HiveQL. When we do the migration, we don't want to change the SQL itself. So we have to have some internal rule to rewrite the query plan to bridge this gap. Then we have an operator to change from the original Hive operator to some shadow operator. This operator has 3 running modes. The first one is the Hive. And it is the production pipeline, same as the current one. The blue box is the Hive task. Then the gray box is the upstream and the downstream dependency. In the shadow mode, we add a new toolbox. It's a branch from the production. The yellow box is a Spark job. The red box is a validation job. No matter yellow or red, they fail, succeed, it's transparent to production. After running for some time, we check the metric, then either switch to the Spark production job or switch back to blue, the leftmost one, that's the Hive mode. In reality, we do hit some issue when we switch to production. Then we have to switch back to Hive, but it's very easy. Just the running mode, change that, then switch back. Not happen very often. We already migrated tens of thousands, maybe 1 or 2, we have to switch back. Okay, assume all the query can run in Spark with correct result. Are we done? Actually, it's the migration framework itself, just a small part of the whole migration project. Assume all those queries, when they are originally written by the owner, each query is tuned by the owner to get good performance. But when we migrate those pipelines from Hive to Spark, we cannot afford to tune each pipeline. It's impossible. Comparing those non-tuned Spark pipeline with the Hive pipeline actually is not fair. What we say actually, if we don't tune them at all, they not perform as good as we expect, sometimes even worse. So this migration part becomes the problem is how do we do the massive tuning and auto configuration for the pipeline. We will give more details on this performance tuning part. The first one is join. In Spark, we already support broadcast join. In broadcast join, if we have table A and table B, if one of them, for example, table B is very small, it can fit into the memory. Then we just scan table A to do the streaming, there's no shuffle and no sorting in the broadcast join. Actually, the overhead is minimum. The second one is the shuffle hash join. Table A and table B, if both of them cannot fit into memory, but for example, B, each partition can fit into memory. Then we can do the shuffle. Then construct the hash map for each partition of B. Then we streaming A. In shuffle hash join, we have to do the shuffle, but we don't need to do the sort. The last one is the sort merge join. In sort merge join, A and B both are big. Even each partition of them are big, cannot fit into memory. This is a catch-all. We have to do the shuffle first. Then we sort both partitions from A and from B. Then do the join step by step. So it has a shuffle, it has sort, and spill. The overhead-wise is the biggest one. We want to avoid if we can apply broadcast join and the shuffle hash join. But it doesn't work out of box for our pipeline. The first one, if you are familiar with it, the statistics estimation based for the current upstream Spark, they estimate the size based on the whole table. In Facebook, we have those pipeline a daily job. The table is huge, but the input data typically is based on some daily partition. The whole table size may be 100x or even 1000x of this real partition data. That partition data is a real input size. If we don't do anything, actually, in our production, we didn't see any advanced join strategy. No broadcast join, no shuffle hash join. Then we also found some memory leak during the shuffle hash join. Actually, it also happened in the sort merge join. The last one we can apply the shuffle hash join. The pipeline running daily, each day, the source data different. If the estimation is not accurate, there's no fallback mechanism for shuffle hash join. It just goes out of memory. This is really bad for production. We can accept slowness. But if today the job is running fine, tomorrow it got out of memory, it's not acceptable. So we do some in-house customized change. First, we add some rule to estimate the real input data size for that partition after the partition pruning, but before the join strategy optimization. After applying that rule, actually we see quite significant number of queries can leverage the broadcast join and the shuffle hash join. After that, we fixed some shuffle hash join, the hash map memory leak. There's another one we fixed. When we do the join, A join B, if we have A join B union A join C, here A is used twice. If both join are in the same join condition, in SparkSQL, in theory, we should scan A only once, but in practice, it's not. Probably dataset API, it will scan once. But in SparkSQL, that part is kind of broken. I think now it's fixed already in upstream, in 2.2 or 2.3. Yeah. OK, combine all this optimization together. This is one of our critical pipeline, part of the query plan. This is a small part. The whole pipeline is much bigger than this. Okay, it's hard. This one, the long blue box, you can see this blue box, it has one incoming edge, but has maybe tens, even 20 outgoing edge. This means this table scan is reused by 20 times. Without reuse, this table will scan 20 times. But in this case, it scans once. Also, here we see we have the sort merge join. This part should be the broadcast join. And the left upper side is the shuffle hash join. We can see all of them combined together. Actually, we get a quite impressive performance gain, at least 2x latency. But without this, it cannot run in Spark. If it doesn't have the reuse exchange, it can maybe run a little slower than Hive. But all of them together, we get good result. We also did some other performance optimization. For example, when we tune the Spark application, typically the partition number is one of the most important parameters. But we have so thousands of jobs. How do we tune the partition number? We have used two heuristics. Our colleague will get some detail, but I give a high-level introduction. We based on the input size. The larger the input, the larger the shuffle data, then we have the larger partition number. But it's not always true. Remember that when we do the shadowing, we retrieve the query from the Hive query log. In that Hive query log, we have the number of mappers, we have the number of reducers. We also have the number of shuffle data. We based on those numbers, then we calculate the partition number for that specific query. All this done is automatically. There's no manual process, so we can scale. We also observe some stage retry. During the fetch failure, during the shuffle data fetch, we observe that if the netty go out of memory, actually we categorize them as the shuffle fetch failure. We retry the stage. It's really bad. The out of memory, that has nothing to do with the shuffle service. Another one we observe that is when we enable the speculation. When the one task finishes, it kills other task. When that killed task is spilling to the disk, it will throw the interrupt exception. This interrupt exception is not handled very well, will cause the executor to be shut down. All the tasks running in the same executor will be marked as failed. If it happens a lot to the job will fail eventually. Another one we want to bring up is the hash aggregate and the sort aggregate. Typically, hash aggregate we expect works better than the sort aggregate. But because our data pipeline is very heavy, it may be shuffle tens or even hundreds terabytes data. Actually, we observe a very high-level hash collision, all those different issues. For some pipeline, we have to explicitly disable the hash aggregate, use the sort aggregate. It provides better performance. Whenever it's not specific to Facebook, we always contribute back to the open source community. Some of them already have the patch. Some of them may be fixed in some other Jira. And this is some high level. Yeah, this is an ongoing project. So far, we have actually achieved very good result. We migrated tens of thousands CPU days from the Hive to Spark. For those latency-sensitive pipeline, typically we can get a very good performance gain. But what's the challenge? Validation is very difficult. Non-deterministic UDF, custom transform. We don't know, because the randomness for the UDF, also the black box of the custom transform. They may write some arbitrary data to some external storage. It's hard to validate. Performance challenge, because we migrate the workload from Hive to UDF or to Spark, so we definitely use Hive UDF. But there's no whole stage code gen support for Hive UDF. If the job is simple, the data conversion between the Hive and the Spark actually dominant. We have to do the wrapper and wrapper for every Hive operator. It's hard to beat Hive for the simple job. And last, the future work, we want to leverage runtime and historical data to get more accurate statistics for advanced query optimization. Then we want to aggressively leverage hash and shuffle hash join. But before leverage that, we have to implement the scalable hash join or some fallback mechanism. If the hash join fail, it cannot fill the job. We have to maybe sort merge join or make it scalable. Yeah, that's all I want to share. Any questions?
Awesome. So if anyone has questions, feel free to come up and ask them at these 2 mics.
So thanks for the talk. So I have a question about Presto. So Facebook also has another distributed SQL engine. So why not using Presto?
Presto?
Yeah.
Actually, we use, just like many companies, we use Hive, we use Presto, we use Spark.
Yeah.
All of them fit into different scenarios.
Okay.
So
what
Presto
is
is very good at interactive. Spark has its own advantage.
So have you compared the performance between Presto and SparkSQL?
Have we compared? Actually, it's query by query. Yeah. For some queries, Spark is much better than Presto. For some queries, Presto better than Spark.
Yeah. So
they fit into different scenarios.
Yeah. What kind of cases you need to use SparkSQL instead of Presto?
Sorry?
Yeah. In what case you need to use SparkSQL instead of using Presto? So yeah, for example, you need sort merge join in your query, so Presto doesn't support
sorry,
it.
I didn't.
So yeah, I'm asking about the actual use case, which is specifically requires SparkSQL instead of Presto.
For example, if we have a very heavy job, we have to spill to disk, all those kind of jobs, Hive and Spark, at least currently, they are more stable.
Okay, got it, thank you.
Okay, thank you.
Two-part question. What version of Spark are you using? And I understand you're in process. You haven't finished this effort. But could you give an estimate of what percentage you've been able, of all the queries you've been able so far to convert to SparkSQL?
Probably I cannot give you the exact number, but as the motivations, the purpose for this migration is identify the gap and move and reduce the computation cost. So far, I think we got a pretty good result. Yeah.
50,
we already mentioned we already migrated tens of thousands CPU days and also migrated some very critical pipeline. But the percentage-wise, probably is a not good place to talk about the exact number. So, thanks for understanding.
Hey, so you took the approach to move your query to run on Spark. As you said, there's another parallel effort to move Hive on Spark, correct? So you can have your default Hive queries and run them on Spark, basically, engine. So there we have a Hive on Spark. You moved your queries to run on SparkSQL, correct?
We didn't use a Hive on Spark. I think.
Yes.
Yeah,
so that's
just
actually my
Spark
question,
SQL.
because like many of the stuff that you already implemented is already implemented in that part, as part of that effort too. So did you guys do the benchmarking, or was there any specific reason for not using that?
You mean not using Hive on Spark?
Yes.
I think it's just a different type of choice. We want to stick to the Spark itself. Once Spark evolved to 2.3, 2.5, we want to move forward together with Spark. But if we use, maybe this is my personal opinion, if we use some other, Spark move forward, we stuck there.
Okay.
Do you know? Okay. Yeah.
So yeah, I have a quick question. So now there are so many different query engines like Presto, Hive, SparkSQL. So I see news Facebook may use Vertica or some other data warehouse That means when people in Facebook, when they query data, they have a lot of choices. They can use all kinds of different SQL. First, it's very confusing how you organize all these different technology in your company and how you make people user experience very, very good or
Typically, we have two types of data. One is the ANSI SQL, one is the Hive SQL. So as we mentioned in the introduction, for our migration, one of the goals is to have the unified interface. So the user doesn't need to be aware of the underlying computation engine, either Hive or Spark. Presto, because it's a total different dialogue, is the ANSI SQL. But if you attend a different Spark session, you can see a lot of companies, actually they use quite different query engine, Hive, Spark, the Presto, in parallel in production.
Yeah.
Because each of them fit into different scenario, at least for now.
So just keep it as is and make people to make choice when they try to query data. So they choose which engine to use.
Yeah, we want to unify them as much as possible. Yeah,
Okay.
But yeah, currently, it's, yeah.
Okay, cool. Thank you.
Thank you.
So there's one more question here before you leave. Hello. It's here.
Oh, okay, sorry.
Yeah. So do you use bucket joins today in Hive? And if yes, what is your experience on Spark?
Bucket join?
Yeah, you create buckets and then you just join the
Yeah,
buckets.
well, I have another colleague, he has a talk this morning. Actually, he worked on that part. We can talk offline.
Okay.
Yes, time is up.
Yeah, that's right.
Okay, thank you.